Here's the video for the day one of the final review for Prob and Stats. Today we're going to review chapters 1 and 2, which is all the probability content that we had covered. Chapter 1 covers counting things, how many ways an event can happen. Chapter 2 uses some of that to figure out probability, which we'll get to shortly. So chapter 1, counting methods, there was two vocab words that ended up being pretty important: permutation and combination. What you need to know about when to use permutations and when to use combinations, since they're both just a button on your calculator. Permutations, we use the button for permutation when we have to have things in a certain order. We use the button for combinations if the order in which we are doing our event doesn't matter, the order in which we choose things. So that's going to be something we'll come back to in a second. For calculating each of the following, 4 factorial, that's the exclamation point. You take the number in front of the exclamation point times all the numbers below it. So 4 times 3 times 2 times 1. So in this situation, we could punch it into our calculator. This is easy enough. 4 times 3 is 12, times 2 is 24, times 1 is still 24. 0 factorial is a weirder one. We have 0 and then all the numbers underneath it, which is just 0. We define that one to be 1, even though it seems kind of weird. That helps us with the next pieces, which is our formula stuff here. So I will show you permutation and combinations here. I'm also just going to show you on the calculator just to refresh you where everything is. But now this next part says 8p3. That's 8 permutations of size 3. So you're picking out of a group of 8 people, 3 people in order. So the order does matter. So what you do for that is you do 8 factorial over 8 minus 3 factorial, okay, which is 8 factorial over 5 factorial, and then we use that to figure out what our answer is. Okay, so you could continue to do it by hand, or you can use the calculator for this, and let me show you. So another way to, sorry, that looked like a times sign, changed it to a minus sign. The number, or the way to punch in permutation, you punch in your 8, you go into your math folder, all the way over to probability. Right here, NPR is our second option, so you can go down and click enter. And I want the number 3 after that. So that would be how you get 8 permutations of size 3. So 336 is our answer for that one. All right, and then give me some room here for 6, choose 2. The formula would be a little bit different for what we're looking to do. All right, it's 6 combinations of size 2. Now order doesn't matter, so that means we have some repeats. So the formula is a little bit different. We have 6 factorial over same thing, 6 minus 2 factorial, but we also have to have the extra 2 factorial on the bottom for repeats. So we could go and try to figure that all out by hand, or we could go to the calculator. So for our calculator here, we're going to punch in our 6. We're going to go to math. We're going to go over to probability, down to the combinations, and we're going to punch in 2. There are 15 ways to do this, to pick 2 people in either order out of a group of 6 people. So that's just a couple ways to find your answers once you get them set up. So now we're going to have to go into trying to solve some actual problems. All right, so now let's try to use it. For each of the following, determine if the situation calls for a permutation or a combination, and then perform the appropriate calculation. In a track team race, there are 9 runners. That's going to be what N is. In how many ways can the first, second, and third place prizes be awarded? So there's 1, 2, 3 different prizes that we're going to award. So this one, order does matter because the person that wins first place cannot also win second or third place. So this would be a permutation, which means we're going to use the P button instead of the C button. So there's 9 people we're going to pick 3 of them. And then we can just go to the calculator for that. Let me get that pulled up here. So we're doing 9 permutations of size 3. And we have 504 different ways that this could happen. Okay. For the next one, it says a committee of 6 is being selected from a group of 25. Yep, 25. Then they want to know how many ways can this be done. So there's not specific jobs for the committee. Sometimes we saw problems that had president, vice president, treasurer, all those things. This is just saying out of a group of 25, how many ways can I get 6 people? So it doesn't matter if you're the first person selected to the committee or the 6th. At the end of the day, you are in the committee. So this is a combination problem. Order does not matter. So there's 25 people to choose from. We're choosing 6 in any order. So again, let's go to the calculator. We got 25. We are going to be choosing 6. An answer of 177,100 ways or different committees that could be formed. So you have to decide if order matters or not. If order does matter, you use the permutation. If order does not matter, you use combinations. Okay. One other thing we did was use a Venn diagram to understand these situations, to understand where there was overlap. And that was something that we talked about sometimes. So if 40 people were surveyed, how many people are in the shaded region? That's our first question here. Okay, well, first off, we know there's 40 people total. In the rock circle, there's 15 plus 7. There's a total of 22 people in the rock circle. So that's 22 plus 4 people that don't like rock or country. So that's 26. So we have to have a total of 40. So we need to have our 40 minus the total that we have here, which is 26, or there's 14 people in this part of the Venn diagram. If you add that up, it should make 40. So we have 22, 36, 40 total. How many people like both rock and country? Well, in a Venn diagram where there's both, that's where you're looking at the overlap. So here, there's 7 people that are in the rock circle and also the country circle. There's 7. So there's more tricky things that we did with our Venn diagram stuff, but for now, that's just a good quick review of what we had talked about. So the next thing we're going to do is talk about Chapter 2, which is going to involve probability. So in Chapter 2, we talked about probability. Again, some vocab that was important. Independent and dependent, and then mutually or non-mutually exclusive. First one's independent events. Independent events means that one event doesn't impact the other. So our best example of independent events was a coin flip. If you flip a coin and you get heads, it doesn't mean that you're going to get heads again for the next one or that you won't. Each coin flip is independent of the next. The next vocab word was mutually exclusive. That meant that the events cannot happen at the same time. So an example of something that can't happen at the same time might be being a 9th grader and being a 10th grader. You can't be both a freshman and a sophomore. So those are just some important words to think about when it comes to probability. Let's look at some examples. All right, first example says, which of the following are not independent? So A, we have rolling a die and flipping a coin. So if I get a 5 on the dice, it's not going to impact whether I get heads or tails on the coin. They have nothing to do with each other, so those ones are independent. Rolling a die 5 times, it should say. Every time you roll the die, it doesn't matter if you got all 4s or all 5s or whatever it might be. You're always going to have an equal 1 out of 6 chance for the next roll. So this one is another one that is independent. So that's that one. Drawing M&Ms out of a bag with replacement versus without. So this is going to be the key here. If you put the M&Ms back in, so if you have a bag of 10 M&Ms, you take one out. If you put it back in, then you're going to be back to 10 M&Ms. That's an independent phrase right there. With replacement is an independent situation. So the last one has to be our answer. Without replacement, so if you take out an M&M and you eat it, now there's only 9 in the bag. The probability of getting a certain color has now changed. That's a dependent situation. Okay, looking at mutually exclusive then. Which of the following are mutually exclusive? Well, drawing an ace or a red. So mutually exclusive means can't happen at the same time. There are two aces that are red, the ace of heart and the ace of diamonds. So this has overlap. You can have both of those happen at the same time, so that's not our answer. So we ask, can it happen at the same time? Can you roll a 2 or an even on a die? Can you roll both of those at the same time? Well, since 2 is even, those both can happen at the same time, so that can't be our answer either. Here's the example I actually came up with. Being a freshman or a sophomore, you cannot be both of those at the same time, so that's called mutually exclusive. So let's look at the last one. It says Mountain Dew versus Mellow Yellow. Well, you can technically like both of those at the same time, so those would have overlap. Okay, so if it's asking about mutually exclusive, you ask, can they happen at the same time? Okay, so this one already has the answer here, but I'll just point it out to you. It says you roll a die 10 times and you get the following results. So it looks like you get 3 a bunch of times right at the end. What is the probability that the next roll will be a 3 and why? Well, here's our answer. The probability will still be 1/6 because rolls of a die are independent. It doesn't matter if we got 100 threes in a row. The probability that you get a 3 on the next one is still going to be 1/3. Okay, so a couple basic probability rules to remember. In a probability model, all the probabilities of something happening must add up to 100%. So the probability that it rains is 60%. That means the probability it doesn't rain has to be 40. Your probabilities have to have a total of 100%. If two events are complements, opposite, they add up to 100. So that's what I was just talking about. Rain plus no rain has to equal 100%. It's either going to rain or it's not. Okay, good there. So this one says the probability that it will snow tomorrow is 0.02. What is the probability that it won't snow tomorrow? So a lot like what I had just done. So the probability that it doesn't snow, so I'll just do snow with a little apostrophe after it, is 100% minus the probability that it does snow, which is 0.2 or 2%. So that would be a 0.98 or a 98% chance that it does not snow. Okay. Then we had these, or this is another example of what we just talked about. So determine the missing probability if the listed outcomes are the only possible ones. Well, what that means is we take a look at what we have so far. We have 0.2 plus 0.1 plus 0.4. Well, that adds up to 0.7. We know that yellow is the only other possibility. So to figure out the probability of yellow, we're just going to do 1 minus 0.7, and we get 0.3. That has to be our answer for yellow because we know if these are the only possible outcomes, they have to add up to 100%. Okay? When probability started getting a little bit more complicated, we added in some rules. Or means add, and means multiply. Okay, so we have to think about that as we go through these as well. This one says, if you flip a coin 5 times, what's the probability of getting all heads? Okay, well, here's what that's going to look like. We have the probability of 5 heads. That's the probability of heads times itself 5 times. You know what I mean. So on these ones, let me just fix that here. On these ones, we have to know what is the probability of getting ahead just one time. And we have to do that 5 times. I know that's only 4 there, but the probability of getting ahead once is 1/2. But we're doing 1/2, and the next one has to be 1/2, and the next one, and the next one, and the next one. Okay, well that's 2 to the 5th on the bottom. 2 times 2 times 2 times 2 times 2. So you could do it that way. Or you could use your calculator and you could do 1/2 to the 5th power. And we could click enter on that. That's not a fraction, but I'll get you one here. 1 out of 32, which is, again, 2 to the 5th on the bottom. So you can answer as a fraction. You could answer as a decimal, which was that 0.03%. Okay, 3%, which is 0.03. Okay. All right, this one says M&Ms claim to have 24% blue, 14% brown, 20% orange, 13% red, 16% green, and 14% yellow. This one says, what is the probability that you pick an M&M at random that would be blue or green? So or means add. So the probability of blue or green is the probability of blue, or means add, plus the probability of green. Well, we know the probability of blue is 24. We know the probability of green is 16. We add those together, we get 0.4, which is 40%. Okay, or means add. If you're drawing a card from a standard deck of cards, what is the probability that you get an ace or a red? So these or problems can get a little more complicated than what I just talked about. So the probability that we get ace or red is the probability that we get a ace plus the probability that we get a red, but there are some red aces. These are called non-mutually exclusive because you can have red aces. There's an ace of hearts and an ace of diamonds. So we have to subtract the ones that are both A and R, ace and red. So there's 52 cards in a deck of cards. With that, there are 4 aces, plus half the cards are red, half the cards are black, so half of 52 is 26. But we counted some more than once right there. So since ace and red could happen at the same time, we have to subtract how many cards are both. I already told you, 2. The ace of hearts and the ace of diamonds. The ace of hearts and the ace of diamonds. So we have a total of 30 minus 2, or 28 out of 52 there. We just don't want to leave that because that's not a simplified fraction. So we could divide that by 4. Divide them both by 4 and you get 7 out of 13. Or you could do 7 out of 13 in your calculator and you could get 0.538 or 53.8%. Okay, so either a decimal of percent or a simplified fraction. Those are the options that are okay. Next up was something called a two-way table. When working with two-way tables, it gives you multiple variables all in one space, but what you need to try to do is you need to try to get the totals right away. That's going to be your smartest bet, which means adding some columns up. So in this, it's people that either had blue eyes or some other color, fair hair or dark hair. So light hair or dark hair. So we want to get the totals of all these, which means add across. So I want to add up everybody that has blue eyes. That's 8 plus 5, which is 13. Everybody that had a different color eye, which is 17. Everybody that had fair hair, which is 8 plus 7. Everybody that had dark hair, which is 5 plus 10. We also want to get the grand total. So if you notice, 13 plus 17 is 30. that's the same as 15 plus 15. So you should get the same number adding down as you do across, right? So we're going to use this table to answer some questions, okay? And there we go, perfect. So we want the probability that we pick somebody with blue eyes. So until we see a special word or symbol, which is toward the bottom of the slide, we need to figure out what the bottom of the fraction will be. It's going to be 30, because that's how many people are there. So we need the total amount of people with blue eyes. Well, that's 13. All right, and the total amount of people that we have total, which is 30. So if we go into our calculator, we could do 13 divided by 30, and that gives us 0.43. So there's a 43% chance that we pick somebody with blue eyes. Let's do a different color for the next one. So the probability that we get somebody with fair hair, that's going to be something out of 30. Well, the total of people we got fair hair was here at 15. So that's 15 out of 30, which is 1/2, which is 0.5. Okay. The and problems aren't so different. Blue eyes and fair hair, that, again, I just told you that means multiply, but with two-way tables, it works out kind of nice. There's one box up here on the top that is both. Here's the box that represents the people with blue eyes and fair hair. There's 8 people that have both. So that's just 8 out of 30, which is 4 out of 15. Or to get a decimal, 4 out of 15 is about 0.267. We usually go to that third decimal place and do our rounding there. 26.7%. If it says or, then we're going to do some adding. And we got to make sure that we don't have any double counting. And if we're careful, then we can get this correct. The amount of people that had blue eyes were 13. So there's 13 out of 30 people that had blue eyes. There was 15 out of 30 people that had dark hair, but there was some people that had both. So the blue eyes or dark hair, when you look at that one, we have to look at how many people with blue eyes had dark hair. That's right here. Those are the people that had both. So we counted those 5 people twice, so we're going to take them back out. So when you do an or problem, check if there's anything you counted twice. So let's see, that gives us a total of 23 out of 30, which is a simplified fraction, so you could leave it there if you wanted. If you want to get your decimal, you have 0.767, and we could say our answer is that, or we could say our answer is 76.7%. Okay, all right, now we're into something different here. So what we have here is the word given popping up out of nowhere. So, or the symbol for given, I should say. So this little bar right here means given, this vertical bar. So what that's saying is, what's the probability that we get somebody that has blue eyes, given that we already know they have fair hair? So now we're not using 30 at the bottom. This number helps us figure out the bottom of the fraction. Okay, how many people had fair hair was 15. Now instead of 30, we changed the bottom of our fraction. The amount of people that had blue eyes in the fair hair part of the table was 8. So if I know that I picked somebody that definitely had fair hair, there's an 8 out of 15, or a 53.3% chance that they also have blue eyes. Let's try that again one more time. The second part, so after the given sign, represents the bottom of the fraction. So how many people had other colored eyes? 17. How many people in this part of the table then had dark hair? 10. So that's the amount of people that have dark hair, given that they had a different color of eyes than blue. 10 out of 17 is 58 0.8%. All right. So that's a couple things to remember. All right, I'm going to talk about tree diagrams here, and then I'm going to let you get to work. All right, so let's take a look at something like this. Okay, and let me clear this out. Okay, so with tree diagrams, you want to fill in the entire tree before you start. You want to remember that to get the and probabilities behind the tree, you multiply down the branches. All right, so for example, in this situation, 0.6 times 0.7 gives us 0.42. And we'll come back to that and we'll finish this tree branch here, but that gives you how many people are male and had school lunch, which we'll get to in a second. All right, so let's fill in the rest of these. Branches of a tree need to make a total of 100%. So if the percentage of people that are male are 60, there's 40% that are female. If 70% of the males ate lunch, 30% did not. If 55 of the females ate lunch, 45 did not. Okay, and then like we said, we want to go get our totals here. 0.6 times 0.3 is going to be 0.18. All right, 0.4 times 0.5, 0.55 is going to give us 0.22. 0.4 times 0.45 is going to give us, it should make 100% total, which we'll check in a second, is going to be 0.18. If you add up all of these four numbers, 0.42 plus 0.18 plus 0.18 plus 0.22, that should make 100%. So every branch all the way down should make a total of 100. So we're going to use these numbers. We're going to see if we can answer these based on what we know now from the tree diagram. First question, what's the probability that a student chosen at random is female? Well, we kind of already answered that. The probability that they're female is already on the tree diagram right here. The probability that we get a female is 40%, 0.4. All right, next question. What is the probability that a student chosen at random is a female and doesn't eat lunch? All right, so that we don't want them to eat lunch. We want female and no lunch. Okay, well, we already multiplied everything here. Female is 0.4, doesn't eat lunch is 0.45. Female and doesn't eat lunch is 0.4 times, oh my goodness, 0.4 times 0.45, which we've already figured out is 0.18, 18%. Okay, next question. What is the probability that a student chosen at random eats school lunch? So to eat lunch, they could either be male or female. So we're going to add the male and eats lunch plus the female and eats lunch. So let's go up and see what we had here. Male and eating lunch was 0.6 times 0.7, which is 0.42. Female and eating lunch was 0.4 times 0.55, which is 0.22. When you add 0.42 and 0.22, you get 0.64. There's a 64% chance that whoever we pick, eats lunch. All right, and last question. Given that the student is male, what is the probability that a student chosen at random does not eat school lunch? Well, that makes this pretty easy. If we know they're male, then we don't have to look at the first branch at all. Now we only have to look at this part, because everything down here doesn't impact us. That's female. All right, so if we know they're male, 0.7 of them eat lunch, which means 0.3 of them do not eat lunch. We want the probability that they do not eat lunch. So the probability that they do not eat lunch given that their male was just 0.3. No math to do on that. So that will do it for the review video for day 1. Go try the quizzes now and ask your teachers what questions you still have.